this is the case when we let sine KL, because to make this to be true, we have two different conditions, right? And this is the first one is when KL equals 2 times m pi, because in order to make this whole thing to be 0, the first one is let sine KL over 2 to be 0. So that's why we let KL to be 2m pi. And this is the case, just use this one to say that sine KL over 2 is 0. And if you use this condition, then we have this result. And the next condition is to let the second term to be 0, because it's sine k over 2 times a bunch of times the result of 2 terms, right? So that's how we're going to go to the next one. This is 29. And the step 6. Another case is to let k over 2 times cosine k over 2 minus sine k over 2 to make this to be 0. And we have, this is the second condition. The one before, we let sine KL to be 0, which is the first term. Now we're going to look at the second term. The first term is easy. There's a analytical solution, because we just have to find out what makes sine KL over 2 to be 0. But the other term, that's not that easy. You need to use numerical methods by plugging the values to make this to be 0, because it's not just one of them, but it's the result of KL over 2 times cosine k over 2 minus sine k over 2. For those of you who know how to use, how to write the programs to solve this problem, and this actually can be solved very easily by assume k over 2 to be x. Then what you need to do is simply to write down, find this function, f of x equals to x times cosine x minus sine x. So this is your Gaussian equation. And the roots, when fx is 0, x is the root. So this can be numerically found, but theoretically it's not that easy. So numerically, if you plug in the values and just try out to see that what will be the values of this, and the first root is numerically found to be about 8.987, something like that, numerically. So you can see that this cannot be found analytically. So numerical solution is the first one. And another approach is you could use the Taylor expansion to find the approximate solution. However, that may not be accurate enough. So numerical solution is always recommended. When KL is 8.9.8, and then PCR can be found. And this equals to actually 80 times 766 times EI over L squared. Okay, is that clear that how this value is obtained? Is that clear? By substituting the definition of K. And if it's not clear to you, remember K is P over EI. So this is the whole thing times L equals to 8.987, right? Then you square everything and move things around. That's how you can get this final answer down here, which is this. Now we have two roots. This is one, the other is the one before, which is this. What's the value of 4 pi squared? Actually, if you calculate the pi is 3.1415965. So this, if you calculate it, I believe is close to 39.48, something like this, times EI over L squared. So for the first root, this is the solution. And the other one is 80.766. So what does that mean? That means this is the buckling load when you have a column buckles like this. Like that. Which is what we already talked about it, the first mode. For the next one, this value is the buckling load of the second mode. Second mode is a little bit challenging. Like this. Now this is second mode. They are both the right answers, depending on which modes you're looking at. Of course, which mode will likely to happen? The first mode. However, in this problem, remember we talked about we have similar discussion last week before. If you introduce additional constraints to this column by introducing a midpoint or midspan constraint. Suppose I add another column here or add another support, which is also the column like this. Right? If you do it like this, and then the first mode will not happen. It will pass the first mode because the kinematic conditions of this column will not allow the first mode to occur. Therefore, the buckling of this column will be dominated by the second mode. Okay, so that's all I got tonight. Any questions? Well, whenever I hear deadly silence, usually means that you're already very exhausted, and you always want. It's already almost 9:30. And if you have questions, you can stay. I'm going to stay here for another 10 or 20 minutes or so. Okay?
Thank you, Professor.
Yeah.
Thank you.
Thank you.
Thank you, Professor.
Have a good night. You're welcome.
Good night. Thank you.
Good night, Professor.
Welcome. Have a good night.
Yeah. Thank you, Professor.
Welcome.
Professor, can you go back to that graph of the stress and L over R again? Sorry.
L over R, that is something here, right?
There.
Yeah.
So I guess my question again is, because so the yielding stress looks like it reaches to this point. So that means that there could be a short column about here that would fail below yield stress.
Yes.
So does that mean that that yield stress should be more like somewhere here?
In fact, you see that when I draw these lines, they are more like conceptual.
Okay.
And
Yeah.
the condition for the short column should be, in fact, if you think about this, let me just clean up this one. Realistically speaking, if materials will fail beyond yielding, you know that the materials cannot take anything above the yield stress, correct? So the actual failure curve, practically speaking, is first you draw the horizontal line. That is a cutoff line. That means nothing can pass the yield stress, which is, of course, to avoid the confusion, I should probably do something like this. You should start from this, right?
Yeah.
And everything above this point is gone.
Mm.
Nothing can exist here. Even so, the curve, the theoretical curve will predict because the theoretical curve is just mass. Mathematically, you can put it in there. But material-wise, you know material cannot go above that. So the actual design curve people use is to use material's capacity. In this case, starting with sigma y, and you just decay it, go down like this. Like this. Of course, there shouldn't be any kinking point at the end. It shouldn't be like this.
Yeah.
Right? And that means materials will not fail. Material, because we're looking at stress, will not fail for the columns within this region. Within here, they will not fail. For designers or for structural engineers, our responsibility is to figure out where's the envelope line, because that's how we check.
Okay.
You just have to be able to establish, and similar to the design spectrum that we use in structural dynamics, we want to know that what is the maximum capacity of the structure. In this case, we're considered numerous combinations of columns because they're different ratios. And be careful here, even so that I already fixed the cross-sectional area, but in reality, the cross-sectional area may change. So what is being holding true here is not always to be a rectangular cross-section, but is the ratio. It's the ratio between length and radius of gyration. This ratio is how we use to distinguish short columns from long columns.
Yeah. Okay. That's why that's all in those tables in the steel manual everywhere. There's a lambda like coefficient and
I can tell you the story behind the use of this ratio. The point is actually to get something dimensionless, because the unit for length is, you know that the length unit, right? And the unit for radius of gyration is also length unit. So L over R is dimensionless.
Yeah.
And the early time when people were discussing or debating over what should we use, some people actually before, they proposed to use lots of different discussions before. Some people use L over L A squared, right? And it's not exactly the same.
Yeah.
And because there are lots of different choices, and they found that this ratio, L over R, actually gives the best indication.